I think we can get started. Um, Let me share my screen. Okay. Hopefully you'll be able to see my screen now. So I just thought I'd bring up the assignments again, just to make sure we're all on the same page. So our expectations about open source, that was just a quiz for 2 points. You've all completed that. Contribution proposals we did last week. I'm going to release the marks for those soon. Process discovery was due a few days ago. It's still officially available because I leave them available for 3 days afterwards. So I'll start marking those soon. And you're all hopefully working towards your contribution to an open source project. And the last thing, just a reminder, although I do have the Slack channels open and I see there's lots of activity there, just a reminder that 20% of your mark will be based on the activity on the Slack channels. Most teams are doing very well on that, so I see lots of activity there. I received a couple of questions around whether everything needs to be documented in pure text format on Slack, or if it's okay to have links there. It's definitely okay to have links there. As long as Slack is sort of the central point from where I can find all the related all the relevant information for your project, all the decisions that have been made, why they've been made, that sort of thing. That's all good. So if you have diagrams or meeting minutes or something hosted somewhere else and put the link on Slack, that's perfectly fine. Like I said, I usually have the Slack channels open. I see lots of activity there, so I think most teams are working well towards that. Okay, before we get into the lecture content, do we have any questions sort of regarding admin aspects of the course? Okay, don't see anything popping up in the chat. Okay, then we'll start with the last lecture before the break. As you all know, we'll have 2 weeks of break coming up. The first one is just officially, no teaching week. The second week is officially university shutdown. So during that time, hopefully none of my colleagues and hopefully also myself have not given you any assignments that are due during that week, because neither you nor us are supposed to be working during that time. And just a reminder, if I remember, I'll post it on my uni at the time as well. The Monday right after the university shutdown is again a holiday. So the next class will actually be on, I believe that's the 29th of April, is that correct? No, 28th, sorry. Hang on. Yeah, 28th. So 26th is a holiday, and on the 28th we'll have the next class after today. Lots of holidays this year. Okay, today I wanted to talk a little bit about deployment, and one reason that I thought that would be good content to cover this week is that many of the GitHub projects that you're going to contribute to use some sort of automation for part of their integration, deployment, delivery, and we'll talk about the differences between these things in a few minutes. So lots of projects have some sort of automation in there. And for those of you who went to the Prax last week, you will have covered GitHub Actions in the Prax, which is sort of GitHub's latest attempt, and so far it's been fairly successful at bringing automation related to what we'll be talking about today into the GitHub platform. And I know that I think actually all of the 3 projects that I picked, I can't speak for the Rust project right now, but I would be surprised if they don't use it. So all of the 3 projects that I picked, Jabref, Pigments, and Settler, they all use GitHub Actions, some more than others, but all use it to some extent. And GitHub Actions are just one way of automating some of the things that we'll be talking about today. It's a fairly trendy subject, so this kind of automation has only been around for I guess the first tools have been around for maybe 10 years, but it's only really been adopted over the last 5 years. GitHub Actions is less than 2 years old. So all of this is fairly new. Chances are open source projects are also still trying to figure out how all of this works. So what we'll be talking about in the lecture today is a bit more of the theoretical background of deployment and how it can be automated. During the pracs last week, you will have played with concrete GitHub Actions to actually automate specific things. And yeah, so that's where this lecture fits into the overall picture. Chances are you'll at least be indirectly users of GitHub Actions as soon as you submit a pull request to any of the 3 projects, because they all use GitHub Actions and most of them are triggered by pull requests. Okay, so deployment. The big picture is how to go from a nice idea or from a nice prototype to actually a really good product. And for those of you who have some industry experience, you will have seen that that might be one of the main differences between what we can do at university and what's actually happening in industry, is that, you know, within a university course, limited resources, limited time, it's usually possible to develop a prototype of something that kind of showcases an idea, but, you know, half of the buttons you better never click on because they might break things. What's different in an awesome product is that, you know, it's thoroughly tested. It's tested on all possible platforms where it could ever be used, and hopefully it works on all of these platforms. It never crashes. Hopefully it also never crashes once new operating system versions are released and so on. So what deployment is really about is how do we structure our software engineering process so that we can go from these prototypes, these things that might, you know, only work on one platform, to these products that actually work on everything. There are quite a few buzzwords involved in today's lecture, and we'll come to the definitions of all of these throughout the next 40 minutes. So you will all have heard of DevOps, which is sort of the marriage between development and operations. And then there's lots of keywords, key phrases starting with continuous. So continuous integration, continuous deployment, continuous delivery, continuous development as well. We'll talk about that. So we'll discuss all of those. I should acknowledge that most of these slides are actually taken from George Mason University, from a really cool course by 2 of my collaborators. George Mason University is in the US, and the slides mostly are the brainchild of Thomas Latosa and Jonathan Bell. In case you ever want to do highly relevant software engineering research, those 2 people know how to do it, and their lab is a really cool place. Cool. What's the software process? So we'll go back to basics just briefly. Software process is a structured activity required to develop a software product. We typically, you know, have specification in there. We have design, we have implementation, we have some sort of validation, and then we have evolution, which is sort of operation and maintenance. And operation in particular refers to, you know, sort of monitoring the software while it runs. And software tools have made this a lot easier just over the last few years now, that, you know, if you have a mobile app running, or if, you know, you have a mobile app and lots of people have downloaded it, most app stores will be able to give you statistics at the very basic level on how many downloads you've had. That's the very basic level. But, you know, the more interesting stuff as well, what errors have people encountered, what particular versions of the operating system are they using, and possibly, you know, which pages have they actually looked at, and so on. So that all fits under operation, sort of monitoring how the product that you've developed is actually being used. And the goal of doing all of this is to minimize the risk of falling behind schedule, minimize the risks related to changes to requirements, and catch bugs and unintended effects of changes early. So if you're monitoring an application that you've developed, and I guess the most basic example is a web application, because those are really easy to monitor. So say you've developed a web application, chances are you have some way of monitoring how people are using that application. What pages are they calling? What inputs are they putting into different fields? What buttons are they clicking, and so on? All the different things that they are doing. It's a really cool way of catching bugs and unintended effects of anything you have in the software, because you can see that maybe 50% of your users went from this page to this next page, and maybe that's expected, but then another 30% went from this page to this next page, and that was something that you never intended to happen at all. And so you can see that there's something going on that maybe wasn't what you had intended. We'll talk about all of this in more detail now. So software specification is the process of establishing what features, services are required, and the constraints on the system's operation and development. You will have heard probably in Software Engineering Workshop 1 about requirements engineering. So it requires, or it includes doing a feasibility study. Can we even do this? Eliciting and analyzing the requirements, then writing down a requirement specification and validating it. So this is hopefully a repetition of what you will have heard in other courses. Software design and implementation is then the process of converting the system specification into an executable system. To some extent, usually you try to do the design first and the implementation next. Doesn't always work that way if the requirements change a lot. So yeah, design the software structure during the design. Historically, this could be done using UML diagrams. Realistically, it's going to be something else. And then the implementation is translating the structure into an executable program. And like it says on the slide, the activities of design and implementation are closely related, maybe interleaved. Okay, software validation is then verification and validation, and intended to show that a system conforms to the specification and meets the requirements. Involves lots of checking, lots of code review, acceptance, and beta testing, where beta testing, of course, means that you give a prototype of your software already to some people, the beta testers, and you hope to get feedback from them. Right. But what we'll mostly be talking about today is then the last step of all of these steps, namely software evolution. As the requirements change due to changing business circumstances, due to moody customers, whatever it might be, the software must change as well. And the way that you can monitor how requirements change is partly through operations. So yeah, we'll get to that in more detail soon. Process models, and that sort of gets us back to, I guess, the name of the course. If we say that we need these 4 steps at least to build software: specification, design, implementation, validation, and evolution, how do we structure our process so that we can do all of these things in some order? This is probably the version that you've done yourself in university projects that we typically do if we just need to write a small piece of software to solve a very specific task. We build a first version and then we just modify it until the customer is satisfied. The customer in those cases is often ourselves. We try it for a while, we see that, oh, this thing doesn't actually work, or this particular step always takes too long, or this button is really ugly. Then we go back and make changes, and at some point, the software is no longer maintained because we have moved on to a new project. Likely, this is the kind of scenario that you will have seen in university courses. You will have followed in university courses where you had to develop a software. You build a first version, and then until the semester is over, you try to improve it, and after the semester is over, you never touch it again. Of course, that process is not the best. It doesn't, allow you to systematically capture new requirements. It's likely not very efficient, and it would make it really hard to work on software with a large team because there's, very little coordination going on. Because of that, it is actually still really common, especially for small products. And the advantages are no overhead. This is really easy to explain, really easy to execute, and you don't really need any expertise related to how to design a software or how to maintain a software. You just stay at that prototype level the whole time. The disadvantage is absolutely no means of assessing progress. You have no idea how far along you are in the software development process at any stage, and really difficult, like I said, to coordinate multiple people. So this works well for hacking, for single-use, personal use programs. Of course, if you just want to write a script to download some data from the internet, you're not going to write a requirement specification and then draw a UML diagram and then come up with a test plan for the script. You're just going to write the script, and if it runs into bugs the first time you run it, you fix the bugs and you run it again until it finally works. So for small single-use personal programs, this makes sense. Then hopefully you will all have seen this, or at least a version of this in another course. So to bring some more structure to all of this, software projects have started to use this waterfall model maybe 30, 40 years ago, which has since then mostly been replaced by Agile. But the idea of waterfall was that we do all of these main steps subsequently, so that we always know how far we are, right? Are we done with the requirements? Are we done with the design? Are we done with the implementation? And so on. So we have that measurable progress. We can hopefully learn from similar steps in past projects. If the requirement specification for our last project was 10 pages long, chances are if we just have a one-pager now, that's probably not a good thing. And it produces these artifacts that can be reused in other projects. So chances are parts of the design at least can be reused across projects. Disadvantage, hopefully this is not news to you at the moment, and that's probably the main motivation then of Agile. It's really difficult to accommodate changes. So the waterfall model is built on this assumption that you can design your entire software before you start implementing it, and that you have all the requirements before you start implementing anything. That's unfortunately not realistic. So that's given rise to various versions of Agile, which results in an iterative model where each iteration is fairly short, usually somewhere between 2 to 4 weeks. And it's really based on this knowledge that requirements will always evolve as you try to build something. And also that likely you'll get more useful feedback from customers if you show them early prototypes rather than just a 50-page requirement specification. So you go through similar steps, but these iterations are much shorter, a couple of weeks usually. So you have some initial concept, which is really just a high-level idea of this is the kind of problem I want to address. You do requirements, you do design, you do testing and operations, all within 2 to 4 weeks, and then you iterate back and do the same thing again for the next requirement. Right, that gets us to the first buzzword, starting with continuous, namely continuous development. What makes continuous development different from Agile is not a lot. They are quite similar. But continuous development on top of Agile has sort of a specific plan for deployment as well. So, like I said earlier, sort of the way to go from an idea or from a prototype to a product is to make sure that it runs on all the different environments with all different numbers of users, all different sizes of the data, whatever it might be, right? Different environments. To do that, you can't really test everything easily within a software company or within a small open source project, but you can deploy it and you can then monitor what happens during the deployment. And maybe you only deploy it to a few people at first. Maybe you deploy it within your company. That works particularly well if you're developing software for software developers, for example. So I guess one example of a project that was probably one of the first to really do this well. Actually, Linux might count as an example as well, because once the kernel was there, they probably ran that kernel to then develop new versions of Linux. But the example I was actually going to use is Eclipse. Some of you might have used Eclipse before. It's a Java IDE that's been around for a long time now. And the developers of Eclipse famously always used Eclipse to develop Eclipse. At least, once there was a first version. Couldn't have done this before there was a first version. But as soon as there was a first version, they always used Eclipse to develop the next version of Eclipse. And then based on Eclipse, IBM about 10 years ago then developed a whole suite of new IDEs related to Rational, Team Concert, and so on, where they use the exact same process. So they developed the IDE in the IDE, which is the best way of testing it, right? Because you're constantly using the product, so you see all the bugs, and you can hopefully fix them in the next iteration and have them rolled out to users in the next release. So that's sort of the basic idea between a staging environment. I think there's a slide on this. Yeah, exactly. So the idea of a staging environment where you sort of run the product, but usually just for a limited number of users. The idea of a staging environment is that as software gets more complex with more dependencies, more things that could go wrong in different environments, it's really impossible to simulate the whole thing with testing. So you can't find all potential issues in a complex software system, especially the kind that gets deployed on many different platforms. You can't find all these possible issues just by writing unit tests. You can find many of them if you deploy things, if you actually make them run in a production-like environment, but maybe not for everybody. So one of the examples there is eat your own dog food, which is exactly what I talked about, that developers might write the software using the software itself, so using earlier versions of the software itself. Doesn't work for all software, of course. The alternative to that could then be to have beta testers, to have alpha testers, so maybe to roll out newer versions of the system, but not to everybody just yet. So, depending on what kind of software project it is, some companies, Google, for example, is a good example, have these programs in place where you can sort of volunteer to test newer versions of the software where they know they haven't ironed out all the bugs yet, but they want feedback. They want to see what works when we actually use this in a production-like environment at a larger scale than what they can simulate within the company. Right, and of course the advantage of this is that if you find bugs in this staging environment where not everybody's using it yet, the cost of fixing it is a bit lower than if you only find the bug once everybody's using it. So yeah, this is kind of what it can look like. So you have your own testing environment, that's what the developer's working with. Then you have a staging environment where maybe a subset of actual users are starting to use something already, and then you have the production environment where a lot more people are using it, and new features or bug fixes sort of get promoted through these different environments. Depending on the scale of your software, you might actually have multiple staging environments in between. So you might have a really small testing environment, then staging environment 1, where maybe some developers within the company are using it, staging environment 2, where you have some alpha testers who get paid to use the latest version, staging environment 2, maybe where you randomly pick a few users from the real world to use a new feature, and then if it has passed through all of these stages successfully, you might actually roll it out to everybody. Right, and that sort of brings us into this area of DevOps, which is, like I was saying earlier, the marriage between development and operations. So in the model that I showed you on the previous couple slides here, you will have seen that deployment isn't just one step anymore. It's sort of become a multi-step thing. So we're not just deploying the final version. We might deploy, a release candidate. That's what they are often called. So a version that has some new features, but that's not thoroughly tested. We might deploy that version to a small number of users. Then once we're happy with that, we'll deploy it to a slightly larger number of users. Once we're happy with that, we'll deploy it to everybody. So deployment all of a sudden has become this this thing that we need to do multiple times at different scale. So if we assume these three environments, we have testing, we have staging, and we have production. Where sort of in traditional software development, you had group of software developers develop something, and then when it's done, it gets deployed, and the developers never see it again until the bug reports come in. Now that deployment has become sort of this multi-step process, the question has come up, whose job is it to do this deployment, or all of these deployments, and how do they interface with the developers? Because chances are the developers can learn a lot from the testing, from everything that has gone wrong in the staging steps, and from everything that has gone wrong and that has been monitored in production. So in the waterfall model, as you can see in the table on the bottom of the slide, the developers had nothing to do with deployment, and all the deployment was done by operators. With Agile, it sort of shifts a little bit. Now the developers do the testing, but the operators still do staging and production. And with DevOps, it's really become a bit of everything. So now people working in a software development company, I'm not going to call them developers on purpose in this case, are in charge of all of this development and operations, because developers, operators, these people responsible for making the software work can probably learn a lot from doing both of these things at the same time. Right. The idea behind DevOps then is to not have development and operations separately. So the people who develop the software are also the people who monitor how it's being run in the test environment, the staging environment, and the production environment, possibly multiple staging environments. The advantage of putting all of this into one is that we have no silos, no walls, no pipelines of responsibility. So you will see that in any software company, the more formal structure you put into place, the longer it takes to actually do something. There are still reasons to put formal structure into place for some things, of course, but it always goes at the cost of time. So if you find a bug during operations, like say something goes wrong in the staging environment, you lose a lot of time if some operators have to find the bug in the staging environment and then find the developer who's in charge of fixing this bug, which can take a long time, and then wait for the developer to fix it. So it's much better, at least that's the idea behind DevOps, if the same person is in charge of monitoring the operation of a product and also fixing the bug. So one team or even one developer owns all the changes, so to speak, from the cradle to the grave. So from the development, from the design, all of that at the very early stages, all the way through to the test, the staging, and the production environment. So one team or one person is in charge of changes to a particular functionality, regardless of the platform. So what we see at the bottom of the slide there is sort of the traditional set up from before DevOps, where you had, particular people in charge of particular functionalities. This example is from Facebook. So you have some developers who are good at messages, some people who are good at events, some people who are good at photos. So all of these, as you would know, are features of Facebook. And then you have other people who are good at Android and other people who are good at iOS. So those are the platforms. That's sort of the traditional way of looking at it. The DevOps way looks slightly different, namely like this. Now all of the people have some expertise in Android and in iOS, and you have one team in charge of messages for everything, for desktop, for Android, for iOS, one team in charge of events for everything, and one team in charge of photos for everything. Assuming that the communication from the iOS experts back to the photo experts would have taken way too long, and it makes more sense for the photo experts to also know enough about Android and iOS to monitor what's going on there. So reducing that kind of silo. That's sort of a quick summary of DevOps. Okay, I promised this at the beginning. We have some definitions for continuous buzzwords. So what are all of these things that I'm sure you will have heard of? Continuous integration is a practice where a developer automatically builds, tests, and analyzes a software change in response to every software change committed in the source repository. And this is an important one, in particular for your contributions to open source projects, because to the best of my knowledge, the projects that you're contributing to all use some form of continuous integration, some more than others, where something will be automatically triggered once you submit a pull request. What that something is depends a lot on the project, and it could be a lot of different things. It could be things like code formatting. Maybe your pull request is automatically getting reformatted, or at a more basic level, maybe the format is just checked automatically and you might get an error message if it doesn't fit the expected format. Maybe the software is automatically built, which means downloading all other components that might interact with the software and make sure that it all compiles together. Maybe some test cases are automatically run, or maybe the change is automatically analyzed to check against the latest security vulnerability database. All of this would fit under continuous integration, and this is something that both in industry and in the open source world is used pretty commonly now in some form. And the keyword here is automatically, right? So this kind of integration has always been done. Test cases have always been run, but before continuous integration, this was a manual process, right? Somebody, maybe a dedicated test team, at the end of the day would trigger the run of some test suites. Maybe somebody would do manual code review to analyze the software changes. So integration has always been done. Continuous integration adds the word automatically to that. And just over the last 5 years, there have been a lot of tools developed that can automate a lot of these things. In general, they work pretty well. There are some issues related to that. But yeah, a lot of this kind of stuff has been automated and to some extent can be automated. And this is something that you will encounter as part of submitting your pull requests. Okay, so that's continuous integration. Continuous delivery is a practice that ensures that the software change can be delivered and ready for use by a customer by testing in production-like environments. Again, this should happen automatically. So this could be a script, for example, that checks out the latest version from a GitHub repository, puts it on a server, and actually runs it there. And then a different question is who will actually be using whatever's running on that server. It could be everybody, or it could be a subset of potential users in some form of alpha or beta testing. Continuous deployment, a practice where incremental software changes are automatically tested, vetted, and deployed to production environments. So continuous deployment goes the whole way. Continuous deployment automatically deploys software changes as soon as they have passed the different test and vetting stages. Okay, this is just a picture of what continuous integration looks like. So going back a step, do we have slides coming up on the other ones? Yes, we do. So continuous integration, the developer puts code into the repository. Some automated tool listens for those changes, and if there's something wrong with the changes, that automated tool notifies the entire team. So this could be, an automated tool that runs test cases, or in this case, I think the example is automated build. So automated build meaning it downloads all the components that the software relies on, makes sure everything compiles together, and probably runs through a few test cases. So that's continuous integration. For continuous integration to really work well, it's important to commit code frequently, because so I mentioned earlier, right? A lot of these things are triggered in the open source world. They are triggered when you submit a pull request. If you only submit one huge pull request at the end of the project, it's only going to get triggered once, which doesn't sound so continuous. So if you commit code frequently, then continuous integration gets triggered frequently, which means it can find issues a lot earlier. You shouldn't commit broken code. Fix broken builds immediately. Developers usually are not happy if whatever's in the main branch doesn't build. Write automated developer tools. So lots of people have done this now. We will have talked about this in the Prax last week with GitHub Actions. There are literally thousands of different automated developer tools now. Some work well, some maybe not quite so well. All tests and inspections must pass. So if as soon as a test case fails, you don't move on to the next stage, which means you can run the builds on your own machine first before you potentially affect the build in the main branch. The open source development model, especially the pull request based model, kind of makes sure that happens. As if your pull request doesn't pass all the different automated checks, then the pull request will not get merged, so it won't affect the main branch. And that's the open source community's way of avoiding broken code. Right, so this is what the pipeline then looks like. You do your local development, commit to version control, build and run tests, and then you deploy to a staging environment. So now we're talking about continuous deployment. Deploy to a staging environment, monitor the software in the staging environment, which bugs actually happen while it's being deployed, what errors have a small group of users encountered, and so on. And once you're happy with how that's going, then you can deploy it to production and continue to monitor. So this is sort of talking about continuous deployment a little bit more, and about some of the time delays that come with that. So continuous deployment, I mean, it sounds like you always have the version running in the production environment that you just committed. That's not entirely true, because there'll still be a few steps along the way, because putting it into the staging environment will take some time. Sometimes just building the software will take some time, and monitoring will take time as well. So there's still some latency involved. A new feature that a developer develops today usually will not be released today, and there's usually one person in the software development team, also in an open source project. Often there's usually one person who's in charge of checking whether a new feature is really ready to go out into the world, or whether more development, more testing, more monitoring should be done. So continuous integration and continuous deployment, so automatically running builds, tests, and so on, and automatically deploying the software, maybe in staging environments, means that thousands of changes come together at once, because if something goes wrong in the staging environment, it could be any number of things. But the way that this is typically dealt with, that software can fail for any number of reasons, is to do all this automation after every change. So this is a number that's actually like 5 years old by now. At that point, Facebook did 20 to 30,000 complete integrations per day for mobile alone. I'm sure by now the number's even larger, because after every change they run all the tests. After every change they build the entire software based on that version. After every change they deploy everything in staging environments. That does cost a lot of money, a lot of resources, a lot of time. You need a lot of servers to actually make this happen. But what the software industry has learned basically is that it makes sense to invest that, because the cost of a bug once it's released to the public is higher than the cost of all these servers, of running all of this stuff automatically all the time. Cool. Something else that you will have heard about is A/B testing. It's sort of a way of, or an example of continuous deployment, I guess. If you have a feature and you don't know whether you want to develop or you want to have it this way or have it some other way, a way forward could be to actually implement both, deploy both to 50% each, and see which one actually does better in practice. So basically monitor in the production environment or in the staging environment first which version people seem to like more. I think Google is famous for doing this a lot. So every once in a while you'll see that your Gmail or your Google Maps or whatever it might be looks a bit different to somebody else's, even though you all have the same browser version and whatnot. That might just be a case of Google doing some A/B testing, where a new feature is deployed to some users but not to others, and they just monitor which one does better, which one, in Google's case probably, which one gets you to click on ads a little bit more. Right, so we talked about monitoring. Let's talk a little bit more about what that actually means. So monitoring is what we'd want to do in the staging environment and in the production environment. So we just want to see how our product actually runs, and there are many aspects to this. So from a hardware point of view, we could monitor how much electricity it actually needs, how hot the CPU gets, how much the fan needs to run, and so on. From an operating system point of view, we could monitor how much memory, how many CPU, and so on the product uses. From a middleware point of view, we could monitor connections, response time, what the database connection looks like, and so on. And finally, from an application point of view, and that's probably the one that's the most important there, we can look at what have users actually done in the software, what transactions have they done. Conversion rate could be how many people have actually ended up buying a product on our website, if that was our product, and the status of third-party components as well. So it really depends on the domain of the software, right? So I've been using Google as an example. Google, as you will know, makes money by selling ads, so they would probably be interested once they make a change if it has affected how many people click on the ads in any way. But they might also be interested in response time, right? Does it take the average user now a little bit longer or a little bit shorter to load a map of their local area? All of these could be things interesting for monitoring. A lot of this monitoring now is, of course, not done manually, but automatically as well. And then if something goes really wrong, then the development team needs to step in, the DevOps team, I guess, and actually fix the bug. this is just one example of what a monitoring dashboard could look like, right? So it could have a list of all the builds. So, you know, maybe the product was able to build successfully on most Android versions, but there's this one particular Android version where the build wasn't successful. So this is something that the developers would want to know and be able to change. You can monitor, you know, different things over time, like disk space, memory usage, that sort of thing. How many database connections are active at any time, which might, you know, tell you whether you need to update the database at some point, and so on. So there are dashboards now that allow you to monitor what a product actually looks like in its deployed form. Right, so to make all of this happen, we need automation tools. Now that it's 2021, we have lots of these automation tools. Like I said, you've been using GitHub Actions in the pracs. The open source projects that you'll contribute to use GitHub Actions. And there are lots of other automation tools as well. So there are tools that automatically build your software or anybody's software by, you know, downloading all the required components, making sure everything compiles together, automatically running tests, build servers, so that's where the build tools then run, and any sort of tool to automatically deploy in different environments. Okay, I think we can skip over the build tools and the build servers. And yeah, I might just finish for today with Travis CI then, which is one of the, as the name suggests, CI continuous integration tools that's used by a lot of software projects, and that is also integrated into GitHub Actions, to come back to that. So the idea, the way that Travis CI, for example, is integrated with GitHub is that it works just as you can see on the slide. A developer commits code to GitHub. Travis CI monitors the GitHub repository, checks for updates, and as soon as there's a new commit to the main branch, it automatically builds the entire project and, you know, will notify the project if anything goes wrong. I think it can even be configured that it would create a new issue in the GitHub issue tracker. And then in Travis CI, you can see which builds were successful, which builds were not successful. As you can tell, usually illustrated using red and green color. Right. And then that brings us to the end of today. So just to summarize, we talked about deployment, and as part of deployment, we talked about quite a few buzzwords such as DevOps, and DevOps really is the marriage between development and operations, or developers and operators, because the software industry has realized that operations, so, you know, actually running the product in an environment and monitoring it, cannot be, or it could be distinguished from development, but it doesn't make sense to do that. It's more efficient to do these things in once. We talked about continuous integration and deployment, which are all automated techniques for reducing time to get features out of the door, to actually get features into the production environment. Staging environment can reduce risks. So instead of deploying something to all users, you might deploy it just within your own company. You might deploy it to some people who have signed up to be alpha or beta testers. Or you might deploy it like an A/B testing to a random sample of all the users that you have. And there's lots of tools available now to help automate this. All right, this gets us to 10 a.m. Any questions before we finish for today? We open the chat window here. Don't see anything at the moment. So if there are no questions, then enjoy the teaching break. Good luck with the contributions to the open source projects. Let me know if you run into any kind of trouble there. and we'll see you again in 3 weeks from today. Keep in mind that the first Monday after the break is still a holiday, so the next class will again be on a Wednesday. All right, thanks everybody, and see you after the teaching break.
Thank you.